And we are live as far as I can see. Yeah, we are live. Let me just give me a moment to share the stream around the media. I'm just gonna write here with big letters starting soon. Okay. I think the quality is fine. We're streaming. Okay. What's going on? Instagram is bugging, but all right. All right, and now let's share it here. Think we're fine. All right. All right. So, ho, everybody. We are going to have a nice live stream today, just like 2 or 3 hours, taking a look at some weird things. I hope some interesting stuff. I will take a look at some interesting facts. Probably we're going to try to find some interesting facts, try to find some interesting data structure. I have found some interesting data structures I want to look at. And yeah, just hang out, enjoy while we can now. And yeah, this is pretty much it. Okay, so first of all, happy holidays, everyone. Happy holidays, everyone, wherever you are. I know we're celebrating New Year's. I mean, it's all different time zones, all different stuff, but Happy New Year as well. If you're already in the New Year, but whatever. Let's start first by directly searching for some weird facts we can look into, and I wanted to first to see if there are any statistics on scientific statistics on scientific papers. So scientific papers, research papers for 2022 in the computer science world. So see if there are interesting statistics we can learn. And if you have in the chat something, you can just post it, interesting blog, interesting thing. Then I will show you very cool repository, but I want to just get the stream going. And then I will show you some very cool things I found. Most cited maybe articles for 20. Let's see. Most cited papers of 2022 in global ranking. Okay. I mean, I'm more interested in computer science. If we can find some interesting, yeah, computer science. Computer science. Yeah, now then we can go, and maybe if you have any recommendation for New Year problems, maybe if you have like new recommendation for problems in the with the theme of New Year, you can post this in the chat as well. Anything is cool. Analysis of list of the highly cited researchers in the Web of Computer Science. No, there's no papers here. Most cited articles, yeah. Let's see. Survey on quantum computing technology, survey deep learning, big data, and Internet of Things, conceptual, empirical. Let's see if okay. I think it's all right. Everything. I think you can see everything. Leveraging deep learning. Okay, so there has been a lot of deep learning stuff. So I mean, machine learning, community detection in node attributed social networks, community detection. So this sounds kind of interesting thing, because it's very connected to graph theory, which I love. During the last decade, yeah. So everyone that's celebrating Christmas, New Year. We here on this channel celebrate interesting data structures and papers. So yeah, it's kind of interesting now. But okay, let's see. The last decade, different ideas and techniques have appeared. In this paper, we aim to describe and qualify the overall situation of the field of community detection and node attributed social networks, namely perform exhaustive search of known methods and propose a classification of them. Okay, this is some abstract idea here. A survey of malware analysis, detection of mitigation of DDoS, detection and mitigation, application of deep learning, retinal image analysis, comprehensive survey of analysis generating methods applicable, mobile content tracing, okay, context aware. So there's most of this is machine learning, as I see here. Most cited articles published since 2019. I mean, I don't know, we'll see. Highly cited researchers 2022 analysis. It's cool to know actually what are the fields of research in currently most cited, because this tells you the influence, and this tells you best paper. Okay, best. Let's see. But this is okay. So there's probably not really. But this tells you what the researchers actually were doing in what were the most common fields of research. Most cited, the most influential papers in 2022. Most influential, maybe I want computer science, because I'm not in top, I mean, AI papers. There is a lot of development in AI, and as we know, ChatGPT and all of these stuff is, I mean, what they did with ChatGPT and with transformer networks as a whole is astounding. The number of parameters that they trained, and these enormous networks that you cannot just put on a everyday computer, right? You need servers and servers and servers to even evaluate something in the network. And then so I mean, it's all very, very interesting for 2022. It's maybe not very, I mean, the expectations were here that we were going to achieve these things, but still the knowledge that a network like ChatGPT can accumulate and can understand is something that is a huge success, even though we kind of were already, like, when Transformers came out, the people knew the attention capabilities of them, right? But this is on a far, far new level, and now they only need to put something to combine these different types of networks into one network that will more like teach itself, and somehow let's see, maybe optimize itself to answer more, like, because ChatGPT is a network that, okay, you can ask it some theoretical questions and it will know the answer, and sometimes will know the answer of questions which are very complicated, but and very specific. But the problem with it's very influenced by the knowledge and the things it has seen. It cannot easily tell you and differentiate sometimes between what is the right answer and what is an answer that it just made up, right? It's like a child. You have, he knows a lot of things, but sometimes he makes up things in order to explain some phenomena. And I mean, there is a very, very big margin of development of these networks, and maybe the network itself needs to adjust somehow to the problems, not just, okay, we're going to train it on like this huge data set of the whole internet knowledge and everything that is on the internet, and then that's it, right? Like, you have, as a child, he has to grow, he has to learn some. This is exactly the same thing. You cannot just do it once and that's it, right? You have to constantly upgrade these networks. And I mean, by 2025, we're going to see something that probably right now I cannot even imagine, or maybe I can imagine it, but I would be surprised to see it. So yeah, it's an interesting thought experiment. List of most important, for just I want to see now here some, like, at least, are there any lists of some papers that are published in 2022 that I can that we can just go through? May 2022 most downloaded articles. Probably, if you know any statistical data, statistical things, statistics for 2022 in science, articles in 2022. Can I filter out some articles? No, I cannot filter out. Also on data science. I mean, 2022 science, just like this, maybe some will pop up. 2022 in science. Okay, let's. I mean, no, this is just the number, or not. What is this? The following scientific events were scheduled to occur. Okay, this is an interesting article in Wikipedia, and there is already on page on 2023. So let's see. Yeah, are scheduled to occur, and now I wonder when they're gonna change it. Let's see. 2022. Let's see, awards. So the Fields Medal in mathematics, yeah, the Fields Medal in mathematics. I mean, yeah, we can take a look at that. Is there something interesting to our stream? Like, is there some interesting computer science things? A physical speed limit for electronic of approximately 1 petahertz is reported. Whoa, that's what, like, billion? Whoa, that's a lot. I mean 10 to the 15 divided by so 10 to the what is 9, right? It's like 10 to the what? 10 to the 6. So 1 million gigahertz. This theoretical maximum is about 100,000 times faster than modern transistor. a physical speed limit. But what does that mean here? What quantum physics sets a speed limit for electronics? So is it like just a limit? It's not being achieved, right? This is some weird stuff. How fast can electronics be? Let me just zoom in here. The quantum mechanical processes that enable this puts a limit to the speed, the signal generation. So they just limit it at that, probably. It turns out that about 1 petahertz is an upper limit for controlled optoelectrical processes. Okay, so they limit it at that. So this is 100,000 times. So yeah, it's quite fast, like a lot, huge. So what we have achieved about what 10 gigahertz? No, we have achieved more than that. Like, I mean, for for transistors, we have probably achieved way more than that. Even though, like, light, if you take about like light's frequencies, like terahertz or something like that. I'm not sure what kind of spectrum, but yeah. What else is interesting here to March in science? So there's March, there's April. Is there, what is computer? So some computer terms. Frontier, yes, is the world's first exascale supercomputer. So the Frontier was built this year, or yeah, exaflops 1 point. I mean, $100 million cost. This is just huge. World's first quantum computer integrated circuit is demonstrated. This is cool. This is cool. Microsoft of an integrated circuit used to control S, but no, this is just an ordinary IC. I mean, why? Okay, so I have to go here. A huge step forward in quantum computer was announced. I actually don't follow a lot of quantum computing, which is kind of, I mean, bad. Like, quantum computing is really powerful, and I know some. Actually, there are websites that you can learn the theoretical aspects of quantum computing via actual real. Is it quantum computers or just simulators of quantum computing? But it's actually really cool. And what he says, this most exciting discovery of the year, a senior author physicist Michelle Simmons. I'm just interested how, if we can start to understand materials at that level, we can design things that we've never been before. So quantum computing, like, I see that doesn't really make sense. This transistor is a small, okay, whatever. This to make this leap in quantum computer, the researcher used a scanning tunneling microscope in an ultra high vacuum to place quantum dots with sub-nanometer precision. Yeah, but is this ice, like, when you place these things, probably they're really unstable. The placement of each quantum dot needed to be just right so that the circuit could mimic how electrons hop along a string of single and double bonded carbons. The trickiest part was figuring out how exactly how many atoms of phosphorus should be in a quantum dot, exactly how far apart a dot should be, and then engineering a machine that could place the tiny dots in the exact right arrangement inside a silicon chip. If the quantum dots are too big, the interaction between two dots become too large to independently control them. Yeah, I mean, Okay, for those who want to read this on, they can, but for a quantum computer, it will only require a processor with 286 qubits. For example, to create a simulation of a penicillin module with 41 atoms, a classical computer would need, well, that's a lot of transistors. That's more transistors than probably what atoms in the universe. Yeah. Yeah, I mean, yeah, cool article. I will now move on from just discussing, I mean, just here, let's see, just a few more events maybe. Let's just, okay, so first quantum computer integrated chip, and then well, we have Samsung announces the first mass production of computer chips using a 3 nanometer process. That's cool. And that's pretty. I mean, there are a lot of achievements. DALI, Chat GPT, OpenGPT-3, OpenAI's different bots, different games, different things. All of these achievements in 2022 are probably huge for computer science and for things going further. But now we're going to move on from this, and we are going to see, we may, if we have time, maybe we can go and experiment something with ChatGPT at the end. But now to the more interesting parts, and that is like data structures, interesting, weird data structures. I found this one article. This one thing I'm just going to find it here because I'm not sure. Yeah, this thing here. Yeah. So this thing here. This thing is a code library by a guy named Shahjalal Shohak, ICPC World finalist, problem setter at the IMO, Code Forces, Code Chef, Hacker Rank, Bangladesh, so from Bangladesh. And the guy has created this wonderful repository here that I can just put a link here. This wonderful repository has a lot of interesting data structures and a lot of interesting algorithms. So I see that there are many forks here, many stars. But what it got my attention is the weird data structures. And when the repository is uploaded? Last year. What it means last year? Probably 2021. Okay. So it's quite a massive repository of interesting things, but there is a lot to go through, and we're just going to chill right now. We're just going to take a look at the data structures, but first I want to tell you something about what are persistent data structures. So our ordinary data structures, I think, are called ephemeral data structures. Ephemeral is stands for lasting for a very short time. So ephemeral data structures are essentially what we all know. Q stack, whatever, like vector, these data structures are DSU, let's say. These data structures are ephemeral, right? So they don't keep memory of what has happened. They're only keeping information for what is the current state. And there is another type of data structures called persistent data structures. Persistent data structures keep memory of what has happened before at some point of time. And these data structures are very important. Such things can be seen in GitHub. Let's say GitHub's versioning system is essentially a persistent data structure because it keeps knowledge of what has happened at some point of time, right? But it keeps this knowledge without saving the whole repository every time we make a commit. It only saves the changes that are in this commit. And these data structures, persistent data structures, essentially do the same exact thing. They don't save the whole state of the data structure. They save the changes that occur after each query. So each query that happens actually makes some changes to the data structure. And if we can save these changes, we can revert back to know how this data structure looked before some operations, before something happened. Okay? And what catched my mind is this here, the what this guy had. Like, this guy had persistent array, which is a very popular, I mean, not very popular, but it's known data structure. Persistent try, I've never heard that. A persistent union find, I'm not sure is that union find with rollbacks, but I have heard of persistent segment tree and a persistent array. But also I have heard about persistent multiple heap, but I never knew what that is. So we have like some cool data structures to take a look at, because we have like here persistent multiple heap, persistent queue, persistent try, persistent union find. This is really cool. Also, queue undo trick is, I have to take a look at that, because this is a very kind of known idea. Okay, that's why I think these data structures are really cool, because you can do things that ordinarily you would think that are maybe even impossible. But with persistency, you can go back in time. You can change. You can rewind the clock, essentially, and do some other changes, and then you grow another branches of these data structures, essentially. But what essentially you have to remember about persistent data structures is about how much memory you need. In persistent data structure, you trade memory for speed ups. You use more memory, but you get huge, sometimes most of the times you get factor of n speeding up on some idea, on some query. Let's say if the query ordinary would take off n time, this will take off log n or something like that, if you have persistency. And so to begin this, maybe it's better to take a look at first at the idea of batched queue. Batched queue, I think CP algorithms, I think that's a nice stop first, before everything gets so complicated that just I'm even myself will leave the stream, right? So first batch queue is something I think CP algorithms has patched queue. No, this is a minimum queue and a minimum stack. Let's say if a bulk queue, a simple batching queue. Groups of random sizes. No, this is some other thing here. I think I think this could be it. I'm just not sure how we modify this. Yes, I think this is what I'm referring to. Yes, with two stacks. So you have one stack and then you have the other stack. Yes, this is what I think we need to take a look at this problem first in order to try to understand how I mean, not persistency for sake, but first maybe it's an easy entry point for beginners to go and to take a look at this queue modification. So this queue modification, I think it's here we consider another way of modifying the queue to find the minimum of 1. So what this essentially, what is the query here? The query is, okay, we added the back, we take it the front, but we always want to know what is the minimum in the queue, if that makes sense. And let's read on to just see what it says. This way is somewhat more complicated to implement, but this time we're going to store all elements, and we are also going we also can remove an element from the front without knowing its value. The idea is to reduce the problem to the problem of stacks. So there are two stacks, and you have one of the stack is on one of the stack you add an element here. When you want to add an element, you add an element and you store what is the minimum element till now. So you add an element and then okay, removing is a little bit more complex because it involves a little bit more things, but okay, let's go one to one. So we will make two stacks, S1 and S2. Of course, these stack will be of a modified form, so that we can find the minimum in of 1. We will also add new elements to the stack S1 and remove elements from the stack S2. If at any time stack S2 is empty, we move all of the elements from S1 to S2, which essentially reverses the order of the elements. Okay, we add here something. When we remove it, the order is reversed. So when we take out from stack 2, actually we take out the first element we have added. So it's essentially a queue in a way, right? Finally, finding the minimum in queue involves just finding the minimum of both stacks. Thus we perform all operations in O of 1 on average. And what is the finding of the minimum? If one of them is empty, we find the minimum of whatever this here there is, and then you minimize if they both have elements, you find either on the one stack the minimum or on the other stack the minimum in the top element. When you add an element, you see where the minimum is, right? It's either on the new element or the minimum of this here. And you add the element. When you remove it, you want to if it's empty, you want to move every element from stack 1. You pop it from there, and then you minimize it with the stack 2's minimum, and then you push it. And this kind of data structure, yes, so we maybe had to first, here in this article, we consider 3 problems. First, we modify a stack in a way that allows us to find the smallest element of the stack in O of 1. Then we do the same thing with the queue, and we'll finally use this, find the minimum of all subarrays of a fixed length in an array. So this is this window, I think, window thing. But this is a great starting point to see that data structures are actually combination of some other things. More complicated data structures are a combination of some other data structures. And we always want to, precisely when you're dissecting, when you're learning about a data structure, you always want to learn about what can the data structure do and in what time it can be done. So how much is the complexity for each operation? And a very important thing in data structures is also memory. How much memory do you need for such an operation? For simple data structures, this is not that important, but for complex and persistent data structures, memory is crucial. Okay, from here we have this minimum stack and minimum queue. Then anyone who wants a bit more on this idea can go to read about sparse table, and there is a wonderful thing about actually that not many people know, that sparse table is actually capable of doing much more things than you might think. Sparse table is based on the way that if you have if you have a function, let me just open up one note. Let me just here open up this. So the sparse table is based on the fact that if you have some numbers, and let's say you want, okay, so what's the difference between the sum function of some numbers and the minimum function of some numbers? The difference in the sum of the the minimum and the sum function is that if you do a sum of some array and then you do a sum of some other array which has an overlapping element or elements, let's say these are overlapping, then the sum function will count them twice. Which means that the sum function is not actually suitable for a sparse table. But if you have the minimum, if you have a minimum function, then you can even though you have an intersection between these two different intervals, you don't actually have to worry about the intersection. because minimum of these elements and you have minimum of the other set of elements of these. So let's draw like this. Minimum of here is actually, if you put minimum on all of these, doesn't matter that they intersect here, doesn't matter. So this is the power of the sparse table and why sparse table can query in O of 1. But as you can see here, there are similar data structures that can handle any type of associative function and range query in O of 1. One of them is called a disjoint sparse table, and the other is a square root tree. So a square root tree is essentially you're dividing in square roots and then in square roots. So, but square root blocks. But I want to take a look at a disjoint sparse table, because disjoint sparse table actually is kind of looks very interesting, and I have never looked at. One more thing about sparse tables is that you can actually create a sparse table in a two-dimensional array. So it doesn't have to be a one-dimensional. You can have two-dimensional array, but the complexity of the sparse table, instead of having like so in a one-dimensional array, the sparse table is known to have n-log n memory complexity, right, and pre-computations. If you have n by n matrix, the computation of the sparse table becomes n times m times log of n times log of m, and this is the memory complexity of the pre-computation phase, and the memory complexity. So the time complexity and the memory complexity. So pre-computation and memory both take this space, and then you can do in O of 1, you can do any submatrix query. So if you have the whole n by m matrix, you can do any submatrix query in O of 1 time if the function is not is this kind of minimum, like this type of function that sparse table actually can support. But the disjoint sparse table, I'm going to just read right now because I have no clue how the disjoint sparse table works, and I want to learn how disjoint sparse table works. So, okay, says he can find the tutorial. He just names it the disjoint sparse table. We're defining. So before defining a structure, dividing into structure, I don't know, and working, let's talk about what it can support. Suppose you're given an array and you're asked to perform Q queries. Each query asks you to compute some function f over some subarray. Now with the sparse table, you can answer these queries in log n with n log n pre-processing. Log n is, essentially, yeah. Let n be 2 to the power of this. Then with this disjoint sparse table, we can answer the queries in O of 1 with, yes. So yeah, with sparse table, if you have like queries on associative function, you can answer with log n time, because what you can do is you can, when you're getting these intervals, you can take out the intersecting interval, let's say, and there's only log n intervals that you need to actually disjoint put together in a normal sparse table. If the function is not this function, idempotent, I think idempotent, the property of certain operations whereby they can be multiplied multiple times without changing the result. Yeah, So this is what this type of property that the minimum function has and the sum function doesn't. Okay, so if a function has this property, then you can answer any queries in O of 1 time with a sparse table. But if it doesn't, you have to log n time. But now we want to make it O of 1 time even for these functions. So let's see how he does it. Its structure is same as segment tree. Okay, each node is related to this. Okay, now consider a node at this interval. So size of the node is equal to R minus L, so size corresponding building. So he essentially pre-computes all of the necessary, as far as I understand. So let's read this carefully. Now consider a node corresponding to some interval L from R, and the middle index is M, so there's middle index. This node stores pre-computed values of what? So the array, the function of the array from I to M, where I is from L to M, and the function from M plus 1 to R, so these two. So the size of the node is equal to the size of the interval. If its size is greater than 1, then it has two children corresponding to these intervals, exactly, right? Now to build a node corresponding to this, we first compute all required pre-computed values of this time. So the size of the interval is what it matters here, okay? Let the time complexity to build a tree with the root of size x be t of x. So he proves that it's logarithmic, okay, which is x n log n. Now to answering the queries. We can answer queries recursively, similar to how we do the segment tree. But here, how do we speed up this to O of 1? Let us say we're in some node. We need to answer the corresponding, then if the middle element is between them, we answer in O of 1, providing we can merge the answers from this in O of 1. Else the range xy is completely in one of the childs. Time complexity of querying would be log n. Okay. Now, how do we improve this? Oh, he improves this with... Oh, no. Let's increase the size to 2 to the power of this, okay? Now consider the jth node at depth I. Consider the binary representation, okay? Now let's say, so there's some binary representation of j, and then there's some zeros, which means the level, the how many levels there are minus what level it is minus 1 zeros. So let's say build a query. Number of leading zeros, okay, whatever, doesn't matter. I mean, so the microprocessor has BSR, bits can reverse operation. We can determine that answer in. So the way he's storing this makes it accessible. We can see that each level sum of size of nodes is equal to n. Yes, so each level sum size is equal. We can simply use a two-dimensional array to store. We can explain with an example. Okay, this is building, and then querying is just finding some things and finding in the table. I mean, this is pretty cool actually. You can try solving sec prog with this. What is sec prog? Prod. Oh, this is a very interesting task. This is a very interesting task. We may try to solve this one here. Given an array A of n integers and an integer p, not necessarily prime, you are required to answer q queries. The ith query is described by two numbers L and R. The answer to the query is the product of the array from the index L to index R. So in this segment, the product of the array modulo p. So we take this product modulo p, and then you can. And then the p is given. P is given beforehand. So p is given beforehand. There's some test cases. P is given beforehand, and there's some huge number of queries. So probably if you were doing just a segment tree, you would probably quickly time limit exceed. I mean, if you have maybe good implementation of a seg tree and like very fast queries, maybe you can. But essentially, this tells you that you have to do some very fast operation in the queries, because 2 times 10 to the 7th query is not small amount of queries. Yeah. The time limit of this task, what does it say? Content time limit 4 seconds, and there's 50 megabytes essentially. Hello Blackboy. Today's stream is a little bit I mean, it's about weird data structures. So data structures that probably no one is going to need, but in some kind of sense of way we can make we can learn from them, learn how they are used, and maybe use their tricks in some more easier problems. And this problem is kind of cool. We can implement this problem using his already written sparse table. Here, sparse table, disjoint sparse table. So what is this disjoint sparse table? Yeah, so he has already this disjoint sparse table, and I may just modify it in order to. Oh, he has this problem. Yeah, this is the same problem, this problem here from code chat. But okay, later that. So I will just first go and take a look at these. Maybe we can take a look at some, like starting from the beginning, because all of these data structures I consider very bizarre, weird, holiday. I don't know, like it's not. I mean, Santa is weird, so yeah. I mean, let's see. Augmented DSU. So this is augmented disjoint set union. We're not going to talk about disjoint set union. Disjoint set union is very well known data structure. But what this data structure, just we're going to take a look at what this data structure allows us to do. Used for maintaining a system of equations of the form x minus y minus x equals d. So what does that mean? Y minus x equals d. That means that if I have two variables, y and x, the difference between these two variables is going to be d. So I want to maintain a system of equations in such a form, right? Along with their consistential queries dynamically using disjoint set union and find data, disjoint set union and find. Okay. Inspired by this problem. Okay, so let's see what the problem actually asks us to do, which utilizes this concept, which can be extended for solving problems of the kind explained above. Okay, let's see what the problem can do, what the problem asks us. There are three kinds of animals, A, B, and C. A can eat B, B can eat C, and C can eat A. So there's a cycle, there's rock, paper, scissors, so nothing actually that much interesting. Now we have n animals, number from 1 to n. Each of them is of the three kinds, A, B, and C. Today Mary tells us k pieces of information about n animals. Each piece has one of the two forms below. So, okay. 1xy, it tells us that the kind of x and y are the same. It tells us that the kind of x and y are the same. It tells us, or it tells us x can eat y. So you don't know which of these. Oh, this is actually interesting. So you don't know which of the animals are A, B, and C. You just know these k pieces of information. You just know either they are the same type, or x can eat y. So you have this. Some of these k pieces are true. Some of them are false. That's even cooler. Now, problem. The piece is false if it satisfies one of the three conditions below. Otherwise, it's true. Okay, whatever. Like x or y in this piece are larger than n. Okay, if they're larger than n, then it's false. I mean, that's clear. Okay, this piece tells us x can eat x. So this information tells us x can eat x, so that's not true. But this information, this piece conflicts to some true piece before. So, okay, x can eat x, definitely it's a trivial check, right? Okay, but this piece cannot conflict with some information previously. But what is the input now? For every block, the first line contains n and k. K lines follow. Each contains three positive integers, d, the type of query, and x and y. Okay, and then what you need to output? The number of false pieces in the corresponding block. So essentially, yes. So essentially some kind of a DSU structure, but why do we need to do? Okay, so I see where this goes. I see where this goes, because what it tells us to do is you have A, B, and C, no? And now if I say some piece and I have some other pieces, and I say, okay, this piece is the same as this piece. And let's say this piece is the same as this piece, and then I tell you about this piece can eat this piece here. So I'm telling you that the difference between, so what he's doing here is he's making, okay, let A be 2, let B be 1, and let C be 0, and he's telling, okay, the A here and this piece, if A can eat B and B can eat C and like this, so the difference between this piece and this piece is 1 modulo 3, because this piece, whatever it is, this other piece is 1 smaller. So if this piece is B, this is C. If this is C, then this is A, because it's 1 smaller than this guy here. So that's why he's using this kind of maintaining a system of equations of the form that this guy here, some x guy, and some other guy, some y and some x guy are in d distance. So some d distance, which is kind of niche data structure, isn't it? It's a very weird data structure. And the ability, okay, so the ability here, it's, we can merge 2 of them. So I say, okay, A eats B and the distance is probably -1 or something like that. Then I can find the root of x, which add all potentials along the path. I need the potential calculated. So there's some potentials here. So we're talking about potentials. So potential is probably something that does not change over the queries. Doesn't change, actually it can change, but doesn't change with the respect in the context of the queries. Let's say if we have, this is number of variables, this number of equations. So he has already solved this problem. So he has okay. So he says, okay, this is the number of variables, this is the number of equations. We initialize for this many variables, and for each equation, one based indexing of variables. So this is one based indexing of variables, okay? And then we assert that the difference of A minus B is D. Queries of type the difference is what can be given through, so he hasn't actually solved, is he? Has he solved the problem? Oh, he has flaws here. So if the difference is not, if the potentials are not D, he has flaws. So queries of the type, the difference between this can be given through the potential, the difference in potentials, only when they are in the same component. They can be extracted from the information so far. Yes, if they're in different components, if I say that, okay, this attacks this one, and then this attacks this one, and I ask you, okay, does this guy attacks this guy here? You don't know that, right? I mean, it could be such that, okay, this guy can attack this guy, but it could be also that this guy can attack this guy. Then, like, they're not in the same component. You have no idea. Okay, so this is a kind of interesting data structure. I won't take a lot of time, but as far as, I mean, that's cool, like to know this, that this exists. This link I gave in the chat. So yeah, this is some guy from Bangladesh, Shahjalal Shohak, made a code library which has these beautiful all these data structures here, and probably just useless, but why not just know that they exist, right? Sometimes you can just solve some problems with data structures, some complex problems with some easy data structure, just copy and paste something. Okay, BIT, this is binary index tree, which is actually a fanfic tree. A binary index and a fanfic tree is the same thing. just two names for the same structure. Two-dimensional with range update and range query. Okay, this is kind of cool because sometimes you need these two-dimensional range updates and range queries, and but this only works on some function that some functions that have the ability to actually do minus operation, to negate the function essentially. Functions which are invertible. I'm not sure how it's mathematically defined, but okay. So this is here. Okay, fanfic tree. I'm not gonna take a look at this. BST using STL. So this is binary search tree using. This code returns a BST, which will create if we add values 1.1 here. Okay, I mean binary search here. Nodes are indicated by values, and every node must be distinct. Nodes indicated by values. So every node has to be distinct. Returns L and R, but why is this even? Why can you just not call it like usual? I'm not getting this structure. I mean, I just called the BST. It's not a big deal. Binarizing a tree. Okay, let's see what is this binarizing a tree. Okay, as far as I know, that doesn't find sen. Maybe it's like finding centroids, centroid decomposition or something. But what is this binarizing though? Oh, there's some query. Oh, there's some problem. Yeah. We love problems, isn't like that's the Let's say this problem is from call force 391, round 391. So this, okay. Let's read this problem. But what we have a sequence of nodes, which is a permutation. Now I want to queue queries of the following type: from L to R and V, meaning bash should report the sum of the distances to this vertex from every other vertex. But yes, the distances from every other vertex to this vertex, where distance is the length of the shortest path. So like, okay, so you want the sum of distances, okay, and then should swap a and x and ax plus 1 in the given. So you swap two numbers, but that they are adjacent numbers. So this actually probably allows him to do some operations. Because when you swap adjacent numbers, what happens when you swap adjacent numbers? Is adjacent numbers always will be adjacent? Will have an edge between them? Or no? Probably not, right? Yeah, no. So there's U and V, there's undirected edges. You have to answer the queries online. So if you see some text like this where you have this previous answer while you get it, and then you modulo this 2 to the 30 power, and then you XOR this. So if you see some text like this, it means that you need to answer the queries online. Well, what that means? It means that you have to answer this query, and the answer of this query, with the answer of this query, you can decode the answer of the next query. Essentially, you don't know the answer, the query, not the answer. You don't know the next query if you don't know the answer to this query. And this is a very common way to do these kind of problems without actually without being them interactive problems. So interactive problems is the same thing. If you don't answer it right now, you cannot know the answer to the you cannot know what next comes, right? What next query comes. And this is the same thing. When you see something like that, just careful with the here with modulo. Here you have to be a little bit more careful, but essentially is this idea of I'm answering this query and then I'm going to the next. You cannot just offline just sort queries and do some stuff like that. You have to, it has to be online. Okay, but I mean, I have to take a look at this problem here, the distances to 1, and then what he does here is he's using some kind of, let's see, he's what binarizing means is, let's see what the function binarizing actually does. So binarizing adds an edge. Binarizing maybe just, okay, TMP, what is TMP? Not sure what it does. I have to look into this. But actually, after binarizing the tree, he's building some centroids, some centroid decomposition, and then he can do these queries about, here the answer is query of root R to U to this guy here. He queries it and then he says, he's just outputting this answer, or he's just updating, swapping here. But I think this problem can maybe be solved with some data structures as a link cut tree, maybe. But okay, we're gonna leave that. A Cartesian tree is a type of tree that it's actually the tree. Tree is another name for tree is Cartesian tree. And Cartesian tree allows you to do some really cool stuff. One of the stuff you can do with Cartesian trees is you can have like so like imagine a set of some array, and what you can do with a tree is in log n time you can just take some part of the array and move it some other way, some like move it like this, and then take like some other part of the array, and you can reverse it, and you can do like this in log n time. I mean, no, that's here, like reverse this, and then and for the array you can have whatever inside. You have more numbers, you can have whatever, and what you can also do is you can do range queries as well. Like you can do sum queries, so you can do sum, you can do range query on any function of the array. So let's say sum product x or whatever. You can reverse range, you can move range, you can, what else you can do? You can delete range, you can add, no, you can't, like you can, all of these functions you can do in log n time. If you want to add a range, you would need to add in the range size. So you add range in size of range. in all size of range. But the how this data, the power of this data structure to do all of these queries in one data structure is extremely powerful. But I don't recommend this kind. I mean, this here, it's not really you cannot edit it. But I have my own, like, I have some implementation of the tree which you can find on github/mitkonikov/competitive. You can go down to tree, and there is this implementation by someone on Codeforces, which is also lazy segment, a lazy tree, and then you can have an example of the tree in the example of the usage of the tree in the task was, what was the task? Transportation. Here I use trip to reverse ranges. So I do my own function here to reverse ranges, and I just reverse ranges this if you want to look how a trip actually is used. Okay, but let's go into another data structure here. Century decomposition, persistent century decomposition. This is now we're getting into I mean, this persistency. I won't take a look at the persistent century decomposition, because century decomposition itself is a huge topic. It allows you to do some things on trees that are just there are whole Codeforces blogs on century decomposition. I'm just not gonna take a look at here. DSU. Okay, what is partially persistent DSU? I want to know this. What is partially persistent DSU? Okay, there's Codeforces problem on the gym. Let's say if I can take a look at this problem. Yeah, I can take a look at this problem. This is from an ACM contest in 2015, actually. Okay. Alex is very clever. Okay, whatever. He gave Alex n nodes and list of queries. Walter then gives Alex one query every second. There are two types of queries: adding an undirected edge from U to V, and what is the earliest time query index. So what is the earliest query when U and V became connected? Two nodes are connected if there is a path of edges between them. Oh, this is really good problem. This is a really good problem, because what the problem, what you can have is like, okay, you can have some nodes, and let's say I connect first of these, so this is one, and then I connect these, this is two, and then I connect these, this is three, right? And then I connect these, like this is four, and these, like this is five, fifth query, and then I ask, okay, this vertex and this vertex, when they first became connected. And they first became connected when this 3 here was initialized. This query 3 was initialized. This edge was created, right? But neither vertex V nor vertex U knows about this edge, because this edge is essentially, the root may be this here, right? So maybe what it looks like is like V here, and then the root here, and then this edge here, and then the other V here, then U, and here, you know. And now how do you do this? So how do you say, okay, so you always, when you have DSU, when you have this disjoint set union, which is very common data structure, you can add things which didn't exist in the data structure. So you can modify the DSU over and over and over and over again. So I had one problem which actually, to show you first an example of such an interesting modification of the DSU is a problem. If we take a look at this and I go competitive and I go IEEE Extreme 60, I will tell you what the problem was. Random mazes, was that the problem? Yes, that was the problem. So the common DSU structure, I got my common DSU structure, and there I needed to add an ability to find if any query had made a cycle into the DSU. So if you have if you have some nodes, and then you say, okay, I have these nodes, and then I connect some nodes. Okay, this node, this node, this node, whatever. Let's just connect them better, maybe like that. And then I say, okay, I will connect this node and this node. I will try to connect. But these are already connected. So the DSU will say, no, man, these are already connected. But I needed to remember that this has happened. This cycle has happened. I don't need to remember the edge. I can't remember the edge. But I can remember the cycle. That this node and this node and this node, this whole tree had made a cycle somewhere. And this is exactly what you can do with just adding a new vector with the ability, with when this cycle is created. When this cycle is created, you mark it on the vector. So if this is the case, the cycle is true, and then you mark that, you propagate this cycle around. And this was actually a nice problem. I mean, it wasn't nice implementation, but a nice problem of modifying the DSU structure to support other types of queries. And this is the same idea here. But what he has here, he has a vector of vectors of pairs. Okay, so I'm guessing for each node, for n of the nodes, he remembers what times this node was somehow connected to some other node. But what is the complexity of the problem? I wonder, is it n squared? No. So you have 10, but when you create an edge, here's the interesting thing about the DSU. The most interesting thing about the DSU is that you will have at most n connections. Why is that? Because at most n times, n minus 1 times, you can connect things. And other connections, I don't care. So I care about the first connections that happened. And this is, and when all of them are connected in one component like this now, that all of them have one component, you can visit every vertex from every other vertex, then you will have n minus 1 connections, and then meaning that you will need to only store n minus 1 things. Okay, so what does this mean here? Okay, so what does this mean? So when you merge this, you add the time, so you increase time, and you say, okay, I get the root at this time, I get this root at this time, and if they're equal, I return 0, I don't merge them. If parent at U, if the last connection on U is bigger than the first connection in V, then we swap them. Okay. Then we push a connection in this time to some other index from U and then to V. So yeah, so what he's doing is, okay, he's saying parent of V equals U, but parent of U is now when does this V came into maybe when let's say how he so he binary searches over the time for each query as far as I can see. So as far as I can see, okay, he merges this and he says at this time this query is I, okay, and then he binary searches if they became same at some time. So if U and V at this time is same, so this is the same idea as persistent fanfic tree. The same idea had the persistent fanfic tree. If I take the root function here, he says, okay, if this is bigger than 0, so he has some pointers here. So he's using pointers in a sense of way to manipulate the data structure. I can't quite understand what he's doing here, but I know the idea. Here. He's here checking if they were the same at this time. Then the answer has to be this, or smaller. Or if they weren't the same at this time, maybe later they became the same. So essentially, if you know, here's another tip. Another weird tip is like, essentially, if sometimes in contests, if you know what the queries how to present the query, then what you can do is you don't need to know how the data structures work, as long as you know how to use the data structures and what the queries are what the data structure allows you to do. So this data structure, as I see it, is some kind of persistency, but because he says partial persistent, because the trick is here that you cannot go back in time and then start from there. You just have to, you just can say, okay, have they been the same at that time? But you cannot just go there and start from there. That's why it's not fully persistent, it's partial persistency. But if you know this, you can just use the data structure in some other problems without actually having to know how the data structure actually works. This is the black box technique. But I mean, now we're just having fun here, just discussing data structures, discussing cool things. You don't have to worry about anything of this in real contests, or like in real contests. If you are allowed to have codes, then you can copy these data structures. If you don't allow to have codes, probably the problems do not require such difficult data structures, and the problems can be solved with easy things. But knowing something about these data structures is kind of cool. It's kind of cool of itself, because it teaches you some things. Another thing here, disjoint. Okay, disjoint sparse table, we talked about this. This is a type of sparse table that the intervals are disjoint. Divide and conquer for insert and query problems. Okay, divide and conquer for insert and query problems. This now is more of the style of what actually can be very common knowledge. Okay, if problems have following characteristics, it can be offline. So if every insert operation were before query operations. So if I insert something at the some operations and then I query and then I never insert it again. Each query operations could have been solved in off-L time. I mean faster than log n. Faster like log n. Okay, I don't know what off-L means, but whatever. Query operation is cumulative, so we don't need every insert at once to solve this query. So it's cumulative, that like when you do something, the structure absorbs it and then it goes further. And it says, okay, problem, you have an empty set. You have to perform the following operations. Insert a given x number x. Count how many numbers in the set is less than or equal to the given number of x. Okay, so this is a very common problem. I mean, very cool problem. All right. But the solution, now we require that the inserts are coming before the queries. Okay, so the operations that we're doing to the array to store numbers, store answers. Okay, this is the answer array. And then we are going to go from L to R. If operations L to R has no queries, we return. So this function takes L to R some indices. If L to R has no queries, we just return. Then we divide that and we say, okay, we're going to first take a look statically built data structure using inserts in these operations. So we're gonna insert these operations. Then I'm going to answer each of the queries for the other operation. So each of the queries from M to R, I will answer them. And then I will solve for the smaller and the smaller on the left and the smaller from the right. So how this looks is that, okay, you have the whole array here. And then you say, okay, I will first see on the whole array, right? So if there are some insert operations that take place here, so in some insert operations that take place here and some query operations that take place here, because we can say that, okay, if I insert some numbers here, I already know a good problem of this, but it's kind of, I don't know, it's kind of unnatural. But so these here operations that are on the left side are contributing to the right side. So that's why he says answer of I is this adding up the query. So because each operation here will contribute something here, because we know that will contribute, because all of these numbers will be smaller than some number x here. And then you go further and then you say, okay, how about on this side, if I add these numbers here, okay, these will contribute to these numbers here, but I don't care about this because I have already computed this. So I have already, if I add some number y here, I have already computed his contribution to all of these numbers, but I need to compute to all of these numbers. And then I go divide and conquer like this. So there will be all log n steps here, and each of the number that I add will be in log n steps called. So each number will be called here, contributing here, contributing here, contributing here, contributing here, contributing here, log n steps. So for each query I have log n, for each of the inserts I have log n. For each of the adding operations I have as well log n. But yeah, some DPs can be solved with this query, but one very interesting problem is called unique occurrences. This problem also can be solved with the divide and conquer. And it's a very interesting problem to hear. And it's you're given a tree with n vertices, and each edge has an integer value on it. Let this be the number of values that appear exactly once on the edges between u and v. So let f of u and v be the number of values that appear exactly one on this path from u to v. Once exactly. So you want to calculate f of u to every other possible v. So from every possible u to every possible v. You want to calculate how many things is. And this is an interesting problem because it involves this kind of divide and conquer. So let's just take a look maybe I have uploaded this somewhere. Let's see. This repository. If I haven't uploaded here, it means it's in the other whatever. I'll just explain tourist's solution quickly. What he has, what's standing? I mean, you have to go here, and then you have to go here. And yes, and then tourist solution for f is essentially a divide and conquer. You can see this DFS L and R, so this is the range from L to R. And essentially what he wants to say is I want to divide and conquer on the queries. So this uses DFS with rollbacks. I mean, it's an interesting data structure it uses, but like I would just leave this problem. I don't know. Like I mean, what he does is it divides it into these, and then for each it adds the edges for the one side. For one of the sides, like adds the edges, and it queries for the other, and then it adds the edges for the other and queries for this side, and then like you do this with rollbacks. You do this non-stop with rollbacks. But it's a difficult problem. I would just not go there. But this is a common technique used in more difficult problems with like dividing and conquering. And then for each of the sides you do something, and then you calculate knowing that other side will contribute to the other side, and then you do for the other side, and then you compute this. For example, doesn't matter. But this is a divide and conquer approach. Another approach is let's see. The divide conquer. Yeah, there's different dynamic connectivity problem is exactly a divide and conquer approach with a persistent this is not a persistent DSU. This doesn't need to be a persistent DSU. This is called a DSU with rollbacks. Yeah, if you want to know about this dynamic connectivity problem, it's stupidly niche problem. You don't have to know this, and it is stupidly niche problem. I was planning a live stream on the dynamic connectivity, but not on this major dynamic, like the general dynamic connectivity on graphs. I was more planning on dynamic connectivity in trees, because this can be more helpful in some way. Dynamic diameter online. So okay, this is diameter of a tree. So diameter of a tree is you have to know what the diameter of a tree is. So diameter of a tree is the longest path between two nodes of a tree. So if I have some kind of tree, and the longest path between any two nodes, so like the longest path, and I suppose the longest path is this here. And you have to know about the diameter of a tree, because actually there are really interesting ideas behind the diameter of a tree. One idea is that, okay, if I find the diameter of a tree, it's always a path. It always will be a path. And the other nodes of the tree will just like make branches here, like this. And this is the interesting idea of the diameter of this. This will be always the longest path, right? And now wherever I am on this here, I can come to the diameter of the tree, right? Like I can compute what is the node that actually is on the diameter. And I can do things here on this diameter because it's a linear structure. I can jump really easily, k steps through the tree. But what is even cooler with the diameter of the tree is like how you find it. You find it by doing two BFSs essentially. Like you start at any node and you do BFS. So let's say I start here. You do BFS and then like you visit here, here, here. Then the next BFS visits here, then the next visits here, and so on, so on. And starting from this node, I don't know if this node is in the diameter or not. I'm not sure, but now we see that it isn't, but whatever. And then okay, actually this won't be the diameter of the tree because like this is even longer than the tree. There will be like, yeah, on the end you cannot have like, the diameter cannot have here some other node because this would have been the diameter. But okay, let's say it's like this. Okay, you start here, you go like this, and then you go BFS, and then you find some other node which is the most distant in the BFS. So how do you find it? You find it if you have like a BFS, while BFS is not empty, you do your usual BFS, and the last node you visited is actually the node that is the most distant from the starting point. The last node always. And okay, and if the starting point was here, the last node, or let's say here, the last node will be most distant is here, and then this you remember as diameter 1, and then you push a BFS from here. Actually, you should create a function for the BFS, and then you start BFS from here, and then you go here. Because you already know that this node is on the tree, on the diameter of the tree, you know that The largest path from this node to some other node is the diameter. So you just go here, you go with BFS, you go through the whole tree, and you find the other D2 node. And then you know that the diameter is between D1 and D2 on the simple path between D1 and D2. And then you can compute some other things. So you can compute some jumpings, you can compute some other cool stuff with the diameter of the tree. That's why he's using here diameter online. So he's just, when you're changing the tree, the diameter changes. So he's just doing some other computational stuff here, but okay, it doesn't matter. Let's go further and see what is this HLD. So heavy light decomposition with persistent lazy propagation, implicit trip. What we call yeah. So this implicit trip, I mean, it's a cool trip. This what we call the Cartesian tree. It's the same. It's some in Russian literature. It's Cartesian tree. Other literature is trip. I don't know. Interval set. Interval set is a very common technique to, if that's the technique. Just affected range of performance. Actually, there is a technique called interval container, but I'm not sure if that refers to an interval container. I mean, I think it does, as far as I can see. Yeah. Yeah, this is assign a value in range in query in the end principle. Assign a value in range in each query, so we assign a value in range. In the end, we print some array of. Yes, this is interval set. This is actually, I don't know, like, let's open up IOI syllabus and see if in the IOI have some, since 2022, interval trees. Okay, so what do we have to know here? Statically balanced binary trees. Creating persistent, what? Is that like in the IOI? Creating persistent data structures by path copying? I thought that wasn't in the IOI. That's too complex. Amortized, yeah, we can make a whole stream for the amortized algorithmic analysis, because this is very important idea. I'm just I want just to see if the legend, where is legend? Okay, so it says included to be defined, included unlimited to be defined, included not for task description, outside the focus. Oh. So this check mark is the most important idea. Okay. So let's go into data structures. Okay, static linked, okay, strategies, elementary, progressing trees, okay, recursion, then we have divide and conquer strategies. Yeah, divide and conquer strategies, and then we have basic algorithmic analysis, algorithmic strategies, algorithms. Okay, then what we have here, data structures, balanced. Yeah, so yeah, this is okay, but this here, I mean, log and time algorithms for answering lowest common ancestor in static rooted trees. Yes, okay, this is the LCA, distributed algorithms. This entire section is question mark. Basic computability. What is this? All topics related to compute. This includes shrinkable meter. rectable problems. Okay, NP hard cannot appear in the. Oh, that does not mean that NP hard problem cannot appear in the IOI. So it means, okay, it can appear in the IOI. Automaton, understanding simple grammar in the Backus-Naur form. Okay, this is, I mean, amortized analysis, of course, this can appear. Geometric algorithms. Software engineering, software design, APIs. I mean, okay, this is not that useful. Okay, so we've left. Okay, we don't know persist. Okay, interval set. Interval set is a type of data structure that actually what it does. It's like, okay, let's get the idea down. You can implement that at home just for the sake, like, because it's it's tricky to be implemented. What is this? Is used in metro maps. What is used in metro maps? Okay, I will tell you about the interval set, but let's see first. I want to take a look at this KD trees. I'll see a link at tree. Okay, this we all know what it is. Monotonous queue is a problem. Stores strictly decreasing or increasing sequence in a queue. Diameter of a tree. Diameter of a tree. I mean, I don't know if it's used in, like, the diameter of a tree is a valuable idea. Yes, if I don't know, like, maybe, yeah, like, I mean, metro maps would be technically trees, yeah. So diameters would exist there as well, yeah. So technically, yes, you would have the diameter, and then you would have like these smaller branches branching out. This is an important idea because what the diameter, it gives you an idea of like how the tree is linearized. It's used somewhere in tasks like, okay, if you want to compute jumping to some, like, if you're in this node and you want, okay, how far, not how far, but like, okay, I want to jump like k stations, right? Let's say I want to jump 5 stations. And then what you can do is you can take a look at jumping through here 5 or through here 5, because you can always find on the diameter of the tree, you can always, if it's not somewhere inside of the branch, like one station, other stations would always be on the diameter of the tree. Why? Because if there is a longer path that, like, let's say existed here, then this won't be the diameter of the tree. This would be the diameter of the tree. And this is very important. Like, it guarantees some specific characteristics about the tree. But I don't know, like, I mean, to know, just theoretically, just to know the idea, it's cool. Because somewhere it may just pop up. And yeah, finding the diameter of the tree is very easy. Just push BFS from anywhere, find one of the nodes, the last node, then from the last node push BFS again, find another last node. Which was just two functions, which one function with one BFS you can find the diameter, and I mean, it's cool. Monotonous queue, as we said, is a queue where you keep where all of the elements are in strictly increasing or decreasing order. Another idea here, yeah. Now we've come to like are the most useful in my opinion. I would say that without stacks and queues, you won't get anywhere. Stacks and queues are something that we all just, even though we don't write it in the back, it happens. Because what actually is, let's say you're writing some DFS function, right? Void or whatever, void DFS. And then you're writing, okay, I'm here, no, this is me, and then this is my parent, right? And in the back, when you call this DFS function, this function gets on the stack, right? This DFS function is called on the stack here. It's me 0, let's say 0 and -1. And then this DFS function calls another DFS function. And then this function calls, and then you're using the stack unwillingly, unknowingly, it's in the back. This recursion takes place on the stack, right? So I cannot argue that queue and stacks are the most important thing, because the most valuable algorithms, DFS and BFS, the traversal algorithms, are meant on the queue and stack. But I would say that also maps, so different kind of binary search trees, maps and hash maps and segment trees are also very important structures, because map allows you to store key value pairs, allows you to, the set, actually storing set of values is built on top of maps, so allows you to do very efficient computations, and the data structures are all built in. So if you are doing C++ or you're doing Java or you're doing anything, everything is built into the standard libraries, and you cannot argue that, like, that's why they're built there, because they're the most useful data structures. Knowing how they work is of vital essence to any algorithm, to any other thing you can imagine, because without a proper data structure, an algorithm is just instructions. You cannot perform instructions if you don't have a data structure to perform on. It's just saying, yeah, I will do this, but I don't have the necessary ingredients to do it. So I will bake a cake, but I don't have sugar, I don't have anything to bake the cake, right? How would you do it, right? And stack and queue is just so powerful, even though they're so simple data structures. You can code them in less than 2 minutes, probably, the whole data structure. There's no no, I don't take donations, donations are forbidden here. It's New Year's and everyone's got his own thing going on, so I'm just doing this for the fun, to just look. No problem with like if you have any other questions about whatever, like dynamic programming, whatever, some like interesting task maybe to solve, maybe, why not just push it down. We can code something, even in Java I can try something, even though Java is very I don't like Java particularly, due to the fact that it doesn't give me that freedom. Always you have to do some things which, I don't know, it doesn't give me the freedom to manipulate memory, to do pointers, to do okay, it gives you pointers, but there's garbage collection and there's things that I don't want to even talk about, and it's slow, and it's very slow, but whatever. I know some of you guys want Java, and Yeah, why not? I will just go here and take a look at. Okay, I will tell you guys about some of the most mind-blowing data structure that there exists. So there exists this interesting idea of, if you have some array of numbers and if you change some number, how can you go back in time? So like you have some numbers and you change some like other numbers, and then you want to go back in time and to see how it looked, right? This is a mind-blowing idea for me when I first heard about this way of thinking. So okay, I have some numbers or whatever, you can have whatever, it doesn't matter to be like numbers, and then like I change some numbers, so and then the array, like after some operation, the array becomes some other array, and then after some other operation, let's say, then the array becomes some other array. And then I can say, okay, this operation is at time 0, this operation time 1, this operation time 20, this operation time 30, let's say, something like that. Then I can go back and say and tell you exactly how the array looked. Some operations beforehand, like say like I want at operation 0 how the array looked, and at this index, like so if you just see it like this, okay, the array looks like this, right? But I will say, okay, what was the at index 3 here? So this is 0, 1, 2, 3, 4, 5. At index 3, what was this number in the first array, in the first time 0, right? And then you can go back and take a look at this number, and this you can done in O of log n, and you can change a number in now it's no longer of 1, so in an ordinary array is changing a number is of 1 and of log n, but now let's say this is like accessing a number. You can do it in log n here, and then here you can do it in of 1 in this ordinary array. But there is like not rollback, but it's called like go back in time, like go back in time. And then you can do this in log n, access any number back in time in log n. Here then you cannot, it's NA, it's unavailable, you cannot do that. So you're essentially doing here more operations, but there is the ability to go back in time, where this here does not allow the ability to go back in time. And here there's more memory, so this is n log n memory plus q log n memory. So for every operation there's log n memory more. Here there's just only of n memory, but the ability to do this data structure, so to be able to do these operations, go back in time, is sometimes vital to some ideas, such as I said, if you go into GitHub, let's say fork, then you can see what was the first commit, what was the second commit. So I can just not show you here in fork. I maybe I can show you in fork here how it looks like if I have like, if I open up fork. Is, by the way, very nice for GitHub, for GitHub management. It's free by it's actually essentially has a paid version, but you can have it for free, and it doesn't have a trial period, so you can have it for free. But if I go here and then I go git competitive. Okay, if I open competitive, let's say, no, and then you can see all of these commits on the competitive repository, right? And then you can go back in time. Okay, this commit, then what I was doing manual practicing, let's say I have solved these problems, right? And then you can take a look at what has changed, how have I implemented this problem. And this ability to go back in time is crucial to here, because if for every commit we were to duplicate the whole array, it would be just huge data, right? Now we want just to save the changes, right? And then go back in time and see how it's changed, right? And yeah, so you can see all of your this, and if you have branches, they're very nicely shown. So this is maybe this I can say is my favorite software that I've learned in 2022. I don't know. Is there a better software I have learned in 2022? Let's take a look at like apps. What apps do I have? Like, probably not. Probably Fork is the coolest software I have learned in 2022. What other softwares do I have here? I don't think I have something interesting. Yeah, what is your what is your favorite software that you've learned in 2022 to share? I don't have anything. There's the difference between GitHub Desktop is that like GitHub Desktop cannot Fork is you can do really powerful stuff with Fork, which you cannot really do with GitHub Desktop. Okay, like GitHub Desktop, if I take a look here, right? So it's the same idea. You have like changes, and you have like branches. You have you can fetch origin repositories, but you cannot really take a look at like do modifications on prior commits as easily. Maybe you can like in history here, but what can Fork do is like can create this like interactive rebasing. This is a powerful option as well. I don't know if GitHub Desktop even has that, like interactive rebasing. Very powerful. There are very powerful options. There are stashes called stashes in Fork, where you can stash things temporarily, and while stashing, you can. Each stash is like a commit, but it doesn't commit it. So it's like just stash. I stash it and then reuse it later if I want to, and what I don't know if that actually is possible in GitHub Desktop. Is it possible to like mark this and like to say, yeah, here for example here is not possible to like, let's say, okay, it's possible maybe to like disjoint here like this, like to say that like, okay, this I don't want to commit it, right? Oh, there are stashes. I didn't know that. Like the UI is just so not nice. Okay, there is this option to do this. To like unmark some changes, but like in here, if I want to go here and let's say let me give, just don't look at this is just totally hilarious, but whatever. Let's say, yeah, whatever. Here No, somewhere that I don't want to. Okay. And then if you want here to, let's say, to remove, to discard changes, you can select whole blocks and say discard here. Or you can select blocks and say stage. This will stage just this change, and then you can commit only this change. So you don't have to commit everything. You just have to commit. Yeah, this is exactly what like you can do with this here, but maybe, yeah. So like if I select like this, it selects my whole change here. But can I? Yeah. So like, yeah, this is exactly what. Yeah. I didn't know that this was actually possible here. It's pretty cool. I mean, it's not as cool as just selecting here, because this here has like more. I know what have I selected, but okay, like, yeah. So I mean, if you use this, is very powerful. These things, these small details are powerful, and yeah. Oh, yeah, it's just a manager. But it's a cool. I mean, for me, it's a very cool software. I like it. I like it very much, and I like the visibility. How I can just order element. How I can just do things here quick. But okay, here as well, it's probably very nicely done. How do you return back to? No, so I just go. Wait, what? Oh, yeah, history. Yeah, history. Go history to see. Okay, I mean, yeah. This is a nice. Yeah, cool. They're both powerful. I don't know. I use it. I use fork all the time, but I didn't. I started at the beginning. I was just using command line prompt, so for me, this was like huge jump, because I was just doing adds, git adds, dot, and stuff like that. Yeah, it's only personal preference, yeah. But what was my point was you can just go back in time. That was my point about this data structure, that you can go back in time. And the data structure that like he has here implemented is based on a tree, actually. And what is this persistent queue though? Why do I need persistent queue? Oh, so for some problem is this. This is some other problem here. Yeah, the persistent queue is again the same idea. You define so as -1 be an empty sequence, so there's an empty sequence, and then you have to do some queries, and then you can define si as the sequence obtained by adding x to the end of some sequence at some time. So this is time ti. At this time you were going back, you're adding onto this sequence an element at the end, and then what you're doing here is define si as the sequence obtained by deleting the front element from some sequence back in time. And yeah, so this is the persistent queue. But actually, like, yeah, I don't know. It's not in the persistent data structure by path copying is in the IOI syllabus. So I mean, but this is not that path copying. This is another technique. Another thing is try. It's an interesting data structure overall. Like try, it's a data structure that essentially, if you have, Try is used in Google search. So it's the most asked. It's one of the most asked interview questions, or some like the most popular interview questions. So let's say we write something in Google search. So let's go Google. Let's go like, let's write persist, and yeah, I do what? All right, whatever. But persistence, no, persistent, and you have this autocomplete, right? So you see an autocomplete if this matches, the first letter matches, and then the most like valuable, like what Google means is like, okay, you're probably searching for this, whatever. Okay, so how do you do this? You do this by you have this huge dictionary, right? You have this huge dictionary. And how do you search very quickly for something that starts on some letters? And sometimes Google knows actually not to. Okay, whatever, but it's something that starts on some letters. And this is done by using try, and try looks a lot, something like this. If you have like a root, and then you have like some other, let's say you have the words car, and then you have the words carpool. I don't know if that's an even word, carpool. What does that mean? An arrangement between people to make a regular journey in a single. Okay. Okay, so carpool, right? Okay, whatever. And then you have like, you have some like pool, like, okay, whatever, like Hajdut. Then you have some other. How do you think life is going if I have a stream on New Year's Day? So like, I mean, so like, okay, so you have car and carpool, and then you have some other word. Let's say it just doesn't start ABC or something like that. And then what you do is you create this kind of structure, this very interesting kind of structure. You start with the one node, and then you add with C, you add like car. This is A, and then this is like R, and then you say, okay, here I'm ending here, and then but there is there is carpool which doesn't end here, which like you can go here car, which actually this R is not here, it's here, carpool, and you get the point. Like you get O, and then you add here, you end here, pool with L, and then you have this like ABC, which it doesn't start on C, so you have like AB C, and then let's say you have like let's say CAP, let's say you have cap, let's say, and then cap would be like here, and here cap would be C, A, and then not R, but you would have like P here, right? And here it ends like this. And then now you have encoded 4 words with much fewer letters. And this is very good when you have like huge dictionary of words. When you have huge dictionary of words, this is very powerful. You can encode very few letters. And this question has been, I think, asked on Google interviews, or maybe not on Google interviews, but on some interviews have asked how Google search autocomplete is that fast. You know, you have this huge array, but actually it's very fast, right? So this is the way why is this so fast? And this is a tree structure that I mean even beginner can code it. It's not that hard. It's essentially it's just one node class which can go somewhere. And this here persistent try is extension on this structure. So a persistent try would be adding versioning. So like here as well, what he has, try version r contains try for 0 to r elements. So when I insert some element into the try, I essentially create a new version of the try. And then I can go back. I can say, okay, remove me these elements or add me these elements or whatever. I can do tricks. Q undo trick is also a I think is a very popular trick, but I have to take a look at these problems. This is problem C on the Baltic Olympiad in Informatics, IOI unofficial mirror. Okay, this is a huge problem. I won't be taking a look at now this, but it uses this. Segment tree structures are also very useful. Segment tree beats is one structure that a Chinese, I think LGM or someone actually invented. And what is very interesting about this structure is actually a very complex structure, but he invented it. Or I don't know, I think it was an LGM who invented the structure. But this is actually proves that even data structures that you think they existed, they should have existed before, do not maybe exist, right? And there are many data structures that will be invented. And this invention of the segment tree beats, I think the segment tree beats is not an old data structure. It's a very, very new data structure. Yeah, so if you take a look at the, it is some Chinese guy invented the thing, historical information. Yeah, yeah. I mean, things can be invented. Here there is a try, there is an ordinary try, but this is only a number try. There are different types of tries, so there are words tries, there's different number tries, there's different types. What the number try actually does, instead of here words, instead of letters here, it actually uses bits. And then you can store any number, any integer with, you know that you can store any integer with somewhere around 30 bits, right? So like if it's an integer, it will have 32 bits. If it's a long, it will have 64 bits. And then this try is its height is only, let's say, 32. And then you can store you can store a set of integers by doing this same operation what we did with carpool and this guy here. But now we don't have like 26 possible things on the first layer. We only have 2 possible things. Either it's a 0 or it's a 1. You store these bits into the try. It's interesting. XOR segment tree. What is this XOR segment? Oh, this is some optimized version of the segment tree. Relevant problem. This is cool that the guy has already relevant problems installed. So, I mean, this problem is problem F on a division 1 plus division 2 round, which means it's a really hard problem. Yeah. And okay. Yeah, so I mean, we took a look at this answer. If we have some tasks we can solve before we go, it's going to be really cool. Also persistent meldable heap is also an interesting data structure, but I have no clue. Yeah, I know that it's used for this case shortage. It's a very popular problem, but I have never seen it anywhere before. Okay, so I'm opening a problem in, what is this, Chinese or Japanese? Let's say, what is this? K-shortest path in easy to implement of the Epstein algorithm. Yeah, probably it's never used anywhere else. Epstein's algorithm is not enough functionality in priority queue to create. Aha, so there's not enough functionality in priority queue to create this Epstein's algorithm. Then you say, okay, you have to insert elements, melt heap A elements into heap B, leave heap A as is, and then add element X to heap A. Aha, so yes, so when as I said, when you dissect these data structures, you have to take a look always at what they do. So what he says is, if I have some heap here and some other heap here, this is A and B, I can add elements on the heap A, so I can add elements here, so I can add elements here. And what I can do is I can have, okay, I have this heap A, I can add all of these elements into heap B. I can melt them into heap B. So melt heap A elements into heap B, leaving heap A as is. And this is in the log of the number of elements. This is log persistent meldable heap can do this. And then here I need to read this. Keep the shortest distance from the leaves in the left child is greater than the shortest distance from the right child subtree. Oh, he's using the oh, I love this. He's using this this technique of median from a stream. This, if you haven't solved this problem, I recommend solving it. I mean, for more enthusiastic people, like median finder is like interesting problem, which probably is the same idea here. But yeah, meldable. Have to look at this. I will just favorite. Yeah, but probably this has no usage whatsoever anywhere else than this problem. Is there persistent meldable heap, randomized meldable heap, randomized meldable heaps and boolean. Okay, for the end of the stream, we may go solve some problems in Edcoder. Some like clear out some like easy problems, maybe just for fun. Maybe solve some easy problems in Java and see like how much time we're gonna need. Randomized meldable heap is a priority queue based data structure in which the underlying structure is also a heap ordered binary tree. However, there's no restriction on the shape of the underlying binary tree. This approach has a number of advantages over similar data structures. It offers great simplicity. All operations to the randomized multiple heap are easy to implement, and the constant factors in their complexity bounds are small. There is also no need to preserve balance conditions, and no satellite information within the nodes is necessary. Okay. Lastly, the structure has good worst-case time complexity. The execution time of the individual operations is most logarithm with the high probability. Yes. Okay. This we know about this. Like this is sufficient analysis. But what is the melt operation? The basic goal of the melt, also called the merge operation, take two heaps by taking each heap root nodes Q1 and Q2 and merges them, returning a single heap node as a result. This heap node is the root node of a heap containing all elements of the subtrees rooted at Q1 and Q2. Okay. The nice feature of this melt operation is that it can be defined recursively. If either of the heaps are null, then the merge is taking place in an empty heap. So melting is just, you get these two heaps, you melt them, you merge them, you get the bigger answer, and then you rotate this here like around, and that's pretty much it. What you do. So like this is not hard to be implemented, but persistency is hard. So like it won't be that hard, but the persistency required is hard. Okay, so let's go and maybe we're now live at 2 hours and 36 minutes. Let's go and add coder. Maybe solve something. So there will be on the add coder 7th, but let's try to solve some easy task in Java, maybe just to get our hands dirty or something. I don't know. Visual Studio, competitive. Input data failure. Thank you for participating. We apologize caused by the problem. We apologize. This entirely responsibility as all questions were created in-house and no sponsor companies were involved. ABC 283, that was the last contest, but normally such incomplete data would result in an unrated rating, but in this case the number of affected people is null. What was the problem though? The number of users who will be affected is small. So we decided to rate them as rated, except for the cases where a different judge status is given only to the test case that has a flaw. We've decided this. So some test case had a flaw. We're unrated. We apologize. What was the flaw? I'm sure. This. I mean, I don't know what was the flaw, but whatever. Let's see what we can do. So if I want to solve a Java problem here, let's say, I don't want to touch this that I haven't solved in, but like, let's say this one, I don't know, let's, okay, whatever. Okay, whatever. Actually, repeats the following: walk at b meters a second for a seconds. Take a rest for c seconds. Walk a meters d seconds. Take a rest when x seconds have passed since they simultaneously started to jog. Which of the actually goes ahead? I mean, it's just I mean, it's not interesting problem to go for Java. Let's say just maths. The string. Okay, this is string problem. Okay, let us call a string. Because wonderful string if the following the string contains an uppercase English letter, a lowercase English. A string contains an uppercase English alpha. Consists of an uppercase alphabet. Yeah, letter, not alphabet. Yeah, okay. It's probably translated wrong or something. All characters are pairwise distinct. So okay. So let's see. I want to know how is this in Java here? How is this OpenJDK 11? Okay. So how is let's say I add this problem. What would I get if I click Java here? I get shit. Okay. I don't get anything. How do I know what class of the problem it is though? Okay, let's try something. So I don't know how even to start. I will just look at some Java things here. What I have here, perfect string, no, not perfect. I had some Java thing. Not this, no, not this. Some Java things here. Where are they though? Maybe if I do Java encoder template. Yeah, but do you need to be named as the class? Like, okay, let's copy this and let's delete this. Do you need to be named as the class? So, so you can rename, so you need to rename what? To rename to this thing here? No, this is terrible. This is terrible. Let's say if I need to do, if I can do this. I told you this stream will get weird. Okay, so you have some scanners. Okay, and I will just. Do I need to close the scanner? That's insane. Okay, let's remove all this. Let's do format document, and let's try to solve this to see if that would actually work. So you have to read this to read a string. Scan dot. So instead of scan, I will just do in here because I'm more familiar with in. In dot next line, maybe, and then I need to say I have no idea how to do this in Java, but like, okay, it's New Year, so I can try some things. Okay, so I have no idea. There is a set, some idea of set, right? Okay, I will show you kids like how it's properly to do this in n time. So okay, so you create a frequency array, and you say, okay, this is 20. Nah, you don't create it like this. You create it like this, 26. Then you go over the string, and then you say, okay, I go over the string. What is happening here? Oh, so you have to do this, right? Yeah, so you go over the string and you say frequency of s of now you get at I, then you do minus a. Is it? There's uppercase and lowercase. So I will just do okay lower, and then I will do upper, and then I can check if scar at I dot no is lower something, or I can just say it's bigger than A, and then scar at I is bigger or equal than Z, then this is lower, frequency lower plus plus, and then I say okay, just so like the mean, okay, frequency at upper plus plus, and then okay, you went through the whole array, you get these numbers, and then now you need to say frequency contains an uppercase, a lowercase, and then so it has to contain both of these. So I will say okay, boolean lower is false, upper is false. I can just do all of these here, and then when I get a lowercase, I do lower is true. Just I know this is too easy, but maybe it's practice for someone. So I get this lower and uppercase, and then I need to see if they're pairwise distinct. How do you check this if they're pairwise distinct? So if the frequency tables do not have only 0 or 1 elements at each of these indices. So boolean okay is lower and upper. So it has to be true, lower and upper, and then you have to go through all of the 26 letters on both of them, and then if frequency of lower of I is bigger than 1, so if it's multiple times some character seen, then okay is false. Also, if that happens to some upper characters, and then you just do system.out.println, and then you try, okay, is it okay? I will print, I think yes, or yes, I will print yes, and then no. Now I don't think my judge here works because yeah, so like okay, so I will just do okay run, and then I will copy the string. Let's see, yes, okay, this is yes. What about this string? This is yes. What about this string? This is no. And what about this string? This is no. So I think this should be correct, but let's say if @coder actually even recognizes this. So it's compilation error. Yeah, I mean, perfect string here, I think it has to be named something else. Error perfect string is public, should be declared in a file named perfectstring.java. How @coder upload Java. Oh, so it has to be named name. I didn't know that. Like it has to be named name. All right, so no, we're just hanging out right now. Like we were talking about weird data structures. We took a look at, I will just send it now, the link just to upload the code to see if @coder accepts it. We were talking about this library here, about this is a library on data structures, on complex data structures, And there are interesting things. We took a look about something about like persistency, some interesting DSU augmentations, DSU upgrades, let's say, or something on this line. And yeah, so I mean, these structures are nowhere to be seen on IOI, on the IOI syllabus here. There is only like create persistent data structure by path copying is like marked as like the very unlikely. It's possible, but very unlikely. But also these binary trees are here, and something tries maybe, but what I mean, the two-dimensional tree-like data structures to the sec trees, tree of trees, this would not be in the IOI. So it depends on what you're looking for. If you are just a competitive programmer who is participating on code forces, this will maybe a useful tool, code library. If you're IOI contestant or chain for IOI, this will be probably not so well good, which won't be. Okay, so we got like AC on this, but it is I'm here like I was trying to, because I don't code in Java, so like Java for me is very unknown, and I code always in C++. So here I got the compilation error, because you have to, apparently, if you're coding in Java, you have to name the class main if you want to be executed in the @coders judge. So this is a cool thing to know, because sometimes Java has this big integer, and if you don't have a big int implementation in C++, you can just switch to Java, solve this problem, and then go back into C++. And this would, knowing different types of different languages is helpful sometimes. Yeah. Okay. So we took a look about this meldable heaps. Meldable heaps are interesting type of data structures. This persistent meldable heap is a very niche data structure. I mean, all in all, the data structures are cool, but probably a lot of them are very niche, for very niche problems and for very niche reasons. So yeah, I don't even know where to start. Probably I will just start here by solving some problems like this, and then going further. If you want to look at some of my solutions and some of my codes and implementations and some tricks, there is like this competitive GitHub things. What is that, YouTube? Okay, that's okay. So here I upload solutions, but most of the things here that are named, let's say, meet in the middle, there is only one problem from Katis here in meet in the middle of this technique, but there actually is multiple problems solved, but there are in different places. So there's some problem here, meet in the middle. Not sure what was the problem. I mean, a couple of problems are here. So with this same technique, so you can search around the repository if you want to see some specific techniques. Maybe just right here some DP. There is a for those who want to see more on dynamic programming and maybe have checked out this educational DP contest, this contest here, I have solved all of these problems. So and I just explain a little bit what's the idea behind the DP state. I just explained this, and then that's it. So that's one more thing you can find in the repository. You can find other DP problems. Yeah. Other than that, I think this is enough for today. If anyone wants to solve to have some tasks solved, maybe we can take a look at it. Other than that, I'll just, yeah, maybe we can solve some task. I want to solve some task. I'm just a little bit becoming hungry right now. It's over 2 hours and 55 minutes already. So meldable. So what should we solve? What should we solve? Should we solve some hard tasks or should we solve some easy tasks? Solve this product. This task is I kind of want to solve this product on segment by module and use his sparse structure here. Let me see. Disjoint sparse table. DST. So he has, okay, so what he has here, he has left, right, okay, goes through the masks, generates this prefix, this probably from the left to from the right position, and then it goes from the left and the right position, and then it multiplies these together with a modulo, and that's pretty much it what he does. So that's a pretty clever data structure. We can modify this data structure to accept any associative function, not just multiplication. But actually, it's too easy to modify this. Just change the multiplication signs here and here, and so you have to define something as neutral element. You have to change this to 0 if you want summation, for example, and then you have this query, and then what do you have here? Yeah, so you have some input, and then LNR, and yeah, this is pretty cool. So this is already I like that. I mean, it's fine. This is fine. I won't modify anything. This is pretty cool. Another thing I wanted to see is the intervals. Interval set. Maybe I should code this once again, because I never liked my my implementation of interval sets. Okay, persistent queue. Persistent queue is built on top of a persistent array, or is it built on top of persistent array? Yes, it's built on top of persistent array. If it's built on top of a persistent array, then like I can build that. I think I have a persistent array. I just need to I don't like how it's this persistent. I like how it's coded. I don't like how it's not in a structure. This is much better code here. This is much better code than what I have here. I mean, here it's like understandable what you're doing. Here it's shorter maybe. But is it understandable? Getting value is fine. When it's building, I mean, okay, this is fine. I mean, this is poorly read. This should be M here, and yeah, I think I like this better. Okay. Cool. Beats, lazy, merging, non-recurrent. Merging? Goes for multiple values. Segment tree merging. Let's see what it is. The problem is maintaining a permutation of 1 to n, supporting range sorting, increasing or decreasing. Query the value of one position after all sorting. All sortings. Yeah, I see. I mean, we just care where this one position has been after all of the sortings. I mean, cool. I think it's fine for today. We took a look into some weird data structures. There are many more weird data structures, static. They're probably a lot more that he hasn't even covered. And we can be probably all night here, just taking a look at different data structures. Let's see this data structure, what it allows. Give you n numbers, helpful get is how many elements in an array are not less than x. Set all elements to x. And reverse. This problem, I think, yeah, it has to be square root decomposition because tree won't work with this query. I don't think so. That's why he has this. Yeah, with reverse update. That's cool. That's cool. That's cool. We're gonna take a look at it sometime. Yeah. He's doing it offline. So I see. I see. He's doing on the queries offline. Yeah. Yeah. I see. I see. Okay. So I think that this will be a wrap up for today. And happy New Year again, guys. Thank you for joining me. If you learned something, just give that thumbs up. Wherever, like anytime you want, just check out my channel. And sometimes I will just stream some interesting streams. If you don't like it, don't like it. Just tell me what I can improve. And yeah, that's pretty much it. Thank you guys for these 3 hours and 15 and 5 minutes. So it's 5 minutes. And yeah, thank you guys so much for watching, and I see you in the next year now.